Remembered. Is Nicholas here? Nicholas, what are we going to talk about in class today? Sorry, say it louder. Sweet. Actually, no, we're not going to talk about solutions to the Proc equation, but that's what I wrote in the pre-lecture reading, so good for you. Good on you for doing it. We're actually going to talk about, we're primarily going to focus on solutions to the Dirac equation. The solutions to the Proc equation are also important, and we will be using them, but they're considerably more straightforward than solutions to the Dirac equation. In fact, just getting solutions to the Dirac equation is half the story. You got to interpret what you've got, and that's going to actually consume us for most of today, if we even get through it all. So I'm not going to lie, it's going to hurt. So let's start. So we want to look for solutions to the Dirac equation, and this is not just an academic exercise without an equation to solve it. These are actually going to play a very key role in calculating scattering amplitudes and decay rates later on, because we have to actually know how the Dirac equation describes particle states that are going into a collision or the particle states that are coming out. So we will use these solutions for the calculations that we'll start learning how to do after the spring break. So what is the Dirac equation, or what are some solutions to the Dirac equation? Well, I'm going to start with the simplest, and I'll derive the simplest, and then I'll just give you the more challenging case, but it turns out to be more useful. So let's assume that our particle, which is described by this four-component Dirac spinor psi, let's assume that it's at rest. So if it's at rest, then we know that all of the spatial derivatives of psi vanish. Okay, the only derivative that will be non-zero is the derivative with respect to time. And so we're going to try to find a solution that describes a spin-a-half particle sitting at rest. And you can alternatively, of course, associate the vanishing spatial derivatives with the momentum, the spatial momentum vanishing. And then our Dirac equation becomes gamma 0 d0 psi plus mc over h bar psi equals 0. Okay? Where normally this would have been gamma mu d mu, but since all of the dx, dy, dz's are 0, those terms won't contribute. The only thing we have is the derivative with respect to time, so we only get gamma 0 contributing to the Dirac equation. And if we recall the form of gamma 0, it's 0 minus I0, where there's 2 by 2 identity matrix hiding here. Okay. And then, of course, this is the identity matrix. Okay. And then what you can do is you can literally, so this is the derivative with respect to CT. Okay, if you don't recall, x0 is CT. So d by dx 0 is d by dct. C is constant, you can pull it out. All right. So these give us then a set of equations for the four components of psi. So if I call the four components of psi, psi 1, psi 2, psi 3, psi 4, then this gives us a set of equations that have to be solved, and I'll just write these out. And the thing to notice as I'm writing these is that they pair up, sorry, that should be 3. Okay, that is literally just plugging in this matrix, multiplying it by this vector of derivatives, multiplying this matrix by this vector of, or this spinor, this four-component spinor, and then just setting each term equal to 0. So I get a series of 4 equations. And what I want you to notice is, and it's a direct reflection of the form of gamma 0, that we're always seem to be pairing up 3 with 1 and 2 with 4. Yeah?
So we're already choosing a gamma naught matrix. If we were to change that to not do what we discussed in class, would the solutions we find be different?
Yes. And that is the reason why this has been a pain in my ass to write this lecture. Because so I had to go through and do all these derivations myself. There was no like just grabbing solutions. And I'm not going to give you the derivation for the non-stationary case because it's a lot of work. I can certainly show it to you. But yes, the solutions will change.
Could you find arbitrary solutions assuming no gamma naught matrix?
No, no, because you can't write this thing down unless you've made a choice. Like you literally cannot write down the form of this 4-component object without some choice of convention. Okay. All right. So the solutions to this come in a set of 4, as we might have guessed, because remember this thing has 4 degrees of freedom. And I will leave it as an exercise to you in your homework to verify that these actually satisfy this set of equations, which you can almost actually see just by looking at the form of the solutions. Okay, so let me write a couple of them down and you'll get an idea. So the first one is going to be e to the minus I mc squared over h bar times time, 1 over root 2, 1, 0, 1, 0. And I just want to remind you that these are the zero momentum solutions by calling them rest, because later we'll look at more general solutions. 0, 1, 0, 1. Okay, so let me point out a couple of things. Even if you don't go through the actual plugging these things in, I can at least point to you why it makes sense that these work. First of all, you'll notice I'm pairing 1 and 3 and 2 and 4 in each solution. And that's kind of what we expect, because the equation should work with 1 and 3 and 2 and 4 separately. Also, you'll notice that there's a minus here, but no minus in here. Okay? That's going to take care of the sign difference that we have here. But down in these solutions, there's no minus here where there is a relative minus sign on the components. Okay? Clearly, when we take a time derivative, the sign in this exponential is going to become an important part of the equation. And that's why, yeah. Okay, so you can literally plug these things in and you will see that they satisfy the equation. Yes?
Should there not be a t in the last 2 equations? Or?
Yeah, I totally left the t out, sorry. That was a lot of writing. Okay? So demonstrating that these actually solve this little set of equations is really and truthfully plug and chug. I don't even know if I will assign it as a homework problem because it's too easy. Really and truthfully. I mean, you guys can take derivatives. I'm going to give you a harder one. Yes?
Are you sure that side 3 is right?
What?
Because when you differentiate with respect to time, you end up with a vector 0, 1, 0, minus 1, and you're adding to it 1, 0, 1, 0, and I'm not sure how that's 0.
Sorry, say it again. When I differentiate with respect to time,
you kick out mc squared over h bar, and then you're adding to it a vector that's 1, 0, 1, 0, because that's side 1. So I'm not sure how that adds to 0.
You're pairing up 1 and 3.
Plug side 3 and
so if I take side 2 and I take hold on.
Look at the first equation, the differential equation.
This one.
Yeah, plug side 3.
This is irrelevant for that third solution.
Is that not side 3?
No, those are the 4
No, these are lower indices. These are the components of psi. These are 4 different solutions. So these things in parentheses mean this is one solution, this is another solution. These are the psi 1, psi 2, psi 3, psi 4 components of psi.
Gotcha. That makes sense.
All right, maybe I should make you verify this. Yes.
Are there any citations?
Are there any what?
Citations for this?
All right, so now, what is very important to notice in this set of solutions is time dependence. Because in non-relativistic quantum mechanics, time evolution of states and if you probably wouldn't have seen this in modern physics, but you definitely will see this in physics 320 if you haven't already seen it in physics 320, okay? But the time evolution of states in quantum mechanics comes from the application of a time evolution operator, which is actually e to the minus I, the Hamiltonian, but in this context we can just take that to be the energy over h bar times time. Okay? And if you want to consult an expert on that, Marie's in the back of the room. But you notice something funny. Clearly, now remember, these are free particles. It's relativity, they're free particles, there's no potential energy, but the kinetic energy of these free particles includes the rest mass energy. These things are at rest, so their energy is just mc squared. So for these two solutions, we're actually seeing exactly the kind of time dependence that we would expect. However, these two solutions seem to be doing something different. All right? Now, it is exactly these two solutions that correspond to the antiparticle solutions of the Dirac equation, where these two correspond to particle solutions. Now, there's a lot of ways that people have tried to interpret the difference between antiparticles and particles. And early on, there were some interesting ideas. Dirac himself came up with this idea that an antiparticle was actually a hole in a sea of these positive energy states, and so it's called the Dirac sea, and it's kind of a useful mnemonic, but it's not really part of the modern interpretation. Feynman and Stuckelberg, a little bit later on, came up with an interpretation that you can think of an antiparticle as a positive energy particle moving backwards in time. Right? The naive interpretation, if you just look at this, is that, oh, well, this is a particle moving forward in time that has negative energy. That way the negative energy would cancel with the negative there. But Feynman and Stuckelberg said, no, we can still use the idea of energy and the positivity of rest mass energy if we instead interpret these as positive energy things moving backwards in time. That sounds cool and interesting. It's not really that interesting. It's only a useful interpretation in terms of implementing this in Feynman diagrams, which is something that we're going to get to, of course, when you come back from spring break. And essentially, it allows for us to interpret in a Feynman diagram where this is the evolution of time, what it means for an arrow to be pointing backwards. Okay, this just says, identify this with an antiparticle. Okay, you don't have to sit and have some deep philosophical conversation about antiparticles being things going back in time, because we have a much more sort of mundane current understanding of it, and that is that the antiparticle solutions actually correspond to particle solutions that have been charge conjugated. What that means is that every internal quantum number is reversed in sign, and that includes the electric charge, as well as some other internal properties. We're going to talk about charge conjugation a little bit later on after we've actually introduced interactions, because right now there's no charge to talk about. So I'm not going to get to charge conjugation today, but that is the best way to understand why these things are antiparticles and these are particles. Okay? But very early on, the form of these solutions was already raising eyebrows, and people were going, well, that's kind of weird. What is that? All right? But remember our counting from last time, as promised, we sort of have these four independent states that we could put our spin-a-half particle in. Okay? Essentially, one of them will be spin up, one of them will be spin down, and we'll have each of those pairs for particles and antiparticles alike. Okay, so last time we were together, we did that counting. We thought we might project down to 2 states from the Dirac equation, but the Dirac equation only projects down to 4. 2 for each particle and antiparticle. Okay? So that's the simple case. Now it's going to get ugly. Unfortunately, or fortunately, when we actually do experiments, we very, very rarely deal with particles that are sitting at rest. Usually they're moving, okay? But the wonderful thing is since we're going to be using a perturbative approach to do calculations, when we're preparing the particles that we're going to have going into some interaction, we can essentially think of those particles as free until they interact. And then we're going to observe particles come out, and if we wait long enough, those particles are going to be behaving as if they're free again. Okay? And the advantage is that we can now talk about these incoming and outgoing particles as having definite momentum. Right? Which is actually something that we typically control. We give the particles in a particle accelerator a certain amount of energy, and we align them with magnetic fields to move along some particular path. So we are controlling, we're fixing, we're setting their incoming momentum. And then in the detector that measures what comes out of the collision, okay, we tend to detect the outgoing momentum. So our calculations to actually compare with the experiment are going to, naturally lend themselves to comparison if we describe incoming states of definite momentum and outgoing states of definite momentum. So we want to try and find solutions to the Dirac equation that are not sitting still like these, but rather have definite momentum. Okay? Well, you're probably all familiar with this from some context, either electromagnetism or quantum mechanics, but what we're looking for then are plane wave solutions to the Dirac equation. The advantage, of course, is that if I actually derive the plane wave solutions of definite momentum, I automatically get these for free, because I could just set the momentum to 0, and I should recover those stationary solutions. So this is a considerably more heinous task than deriving these. You could actually sit down and play with those differential equations I had up here for a bit of time and extricate the form of these solutions. This is a more tedious process, so I'm just going to give you the solutions. First of all, we're going to start with a plane wave ansatz. So we're just going to have some overall amplitude, which we can take to be a normalization constant to be determined later on. This is a relativistic form of a plane wave, so you see the usual wave vector times the spatial coordinate vector. Here it's a 4 wave vector and a 4 spatial vector, the e to the minus I kx. And then this is a scalar, but I'm looking for a 4-component spinor, so I'm going to put the 4-component spinorness of this thing over here. Okay? Remember that this is sort of the overall motion of this thing, and that's somewhat captured by the Klein-Gordon equation, which we talked about last time. The fact that this is actually a 4-component object as opposed to just a scalar is sitting in here. Okay? So the Dirac equation is going to tell us something really interesting about this. Yes?
Typically, in a plane wave solution, we would have kx minus omega t is the t information, so to speak, in the x mu.
Yeah. I mean, kx minus omega t
Right.
is, so omega we often associate with what?
I'm not sure if this is.
So can you relate k and omega? So k, if you're for example talking about light, then k is 2 pi over lambda, but lambda f is c,
Right.
and f is 2 pi. Yeah. So you're seeing exactly that form. Okay. I'm just not going to break it down into space and time. Okay. So the first thing that you can do in the derivation of this is notice that if you take the derivative with respect to all of the coordinates, this just gives me minus I k mu times psi. Okay, that's taking the derivative with respect to the spatial coordinates. So I'm just taking the derivative with respect to x, that pulls down this factor. But then if I plug this into the Dirac equation, this is where I'm never going to get my sign right. Plus or minus, guys, you plus, right? Okay, if I plug this into the Dirac equation, then what I find is that this reduces to I h bar. Yeah, I'm just pulling the h. I'm just going to pull the h bar back over in front of the other term. Gamma mu k mu minus mc acting on psi 0. Okay, I just pulled the h bar back up in front of this term. The I now appears because I'm taking the derivative, and I'm pulling a minus sign down because I took the derivative, but I'm transferring the minus sign over to this term, which I can do because everything's equal to 0. But what you notice about this equation is that there's no derivative in it. Everybody see that? Dirac equation, derivative. This equation, no derivative. This is algebraic. So you are now to find, this should actually be, yeah, we can do this side. Okay, you can actually now solve this thing not as a differential equation, but as an algebraic equation. Now, it's not a simple algebraic equation. I wish, we could throw this at Physics 100 students and have them solve it, but that is not going to happen. Okay? And in fact, I'm going to skip all of the work, but again, if you're really interested in the details, I can show you. Griffiths does it. You can look at Griffiths' derivation if you have the class book. Kind of makes some sense. Unfortunately, with these conventions, the derivation and the solutions that we get look very different than what Griffiths has. Okay? But nonetheless, you can solve this thing, and the first thing that you notice when you solve it is that the form of k mu, this wave vector, is forced to be plus or minus 1 over h bar times, and I'm going to say k with an upper index. You can, of course, if you have k with a lower index, you can always form k with an upper index, but the wave vector has to be proportional to the 4 momentum vector of the particle. Okay, this is part of solving this algebraic equation, all right? And you can see that same result come out of Griffiths' treatment. But with that in mind, we end up getting the following 4 solutions. Okay, notice my k I've just replaced with, in each of these, it'll be replaced with either plus or minus 1 over h bar p mu. Don't write that down. I looked at the wrong one. Sorry. And the upshot for you of me actually writing these solutions is that you're going to get to prove these solve the Dirac equations. I derived them. The least you could do is show that they solve the damn equations. And then last but not least, side 4. Now, something I totally forgot to say when we started out, and I'll say it now. So, I said earlier that these are going to correspond to particle, antiparticle solutions, and then I alluded to that this would be maybe like spin up and spin down, spin up and spin down. But let's actually see the connection to spin up and spin down. So first of all, if I want to do spin up and spin down, I got to know what is the form of the spin operator, say along the z-axis, as it acts on spinors, 4-component spinors. Okay. Well, we know what the spin operator looks like when it acts on 2-component spinors in quantum mechanics. It's just 1/2 sigma z, or h bar over 2 sigma z, where sigma z is the Pauli matrix. But in this case, and we actually worked this out much earlier on when we calculated what sigma mu nu looks like. Okay, these are the generators of boosts and rotations. So if you look at a rotation in the xy plane, that corresponds to the rotation around the z-axis. And it's actually just this combination of the sigma matrices. So we actually covered that early on, yes.
So going back to 3 and 4 real quick. So in 1 and 2, it's kind of doing what we expect it to do, where like 2 has like 0 in the 3, but 1 in the 4. How come it, and then same for 1, but it doesn't do that in the 3 and 4 case where it does for psi 4, there's a 1 in the psi 1 spot, but no in the psi 2 spot. Because I feel like the psi 4 and psi 2 should still be paired by.
You feel like psi 4 and psi 2 should still be paired.
So like in the rest case, there's a.
Okay, so let's just compare. Okay, I mean I was going to say this a little later, but let's just compare. So let's take this solution and ask what does it look like in the rest frame. Okay. In the rest frame, all the p's are 0, right? And in the rest frame, e is mc squared. So this becomes 1, 0, minus 1, 0.
You have an A there, it's arbitrary.
No. I want to make sure I wrote these things down right.
You've got the A, you can just absorb the negative one.
Oh, yeah.
No. Maybe I wrote down my size initially wrong. Yeah, that's a distinct possibility. Psi 4 is minus 1.
They're off by negative. Yeah, the exponential.
Yeah, there. So yeah, I mean they're off by.
One of those has a negative sign.
Yeah, so I'm gonna come over here and do this. I'm gonna do this. I'm gonna call it a day.
Okay.
Yeah. Now are we okay? Now side 3 doesn't agree. Oh man, you guys are killing it. So side 3 is 0, 1, 0, minus 1. Oh, yeah. Yeah, that's fine. Yeah, okay. So now we're fine, right?
Yeah.
Okay, yeah. It was me making a mistake writing down the signs here.
The exponentials have different.
Now the exponentials have the right sign dependence. Okay, you might be looking at it saying, wait, this is negative and that's positive, but remember in the rest frame, P mu is minus mc squared 0, 0, 0, 0. Okay, so when you combine that with the CT here, that cancels the minus sign, giving you the positive exponential time dependence. Right? Yeah, Mark?
So before when you had the K mu and the P mu up there, I understood that why it looks like that, but why do we have K mu equals plus or minus 1 over H bar P mu?
Why do you have it?
Why would there be a minus? Because like in standard quantum, it's just P is H bar K. So it makes sense that you would get.
So the only thing that you can show has to be the case from the content of the Dirac equation itself is essentially that k mu has to be equal to 1 over h bar squared p mu.
Oh, so
That their squares are equal.
Okay.
And that means that if you're just looking at the vector itself, it can be plus or minus.
Okay.
So remember, we're doing relativistic quantum mechanics, so everything starts out squared.
Yeah.
Like e squared minus p squared equals mc squared, versus starting out with some assumption that something is, linearly related to something that's quadratic, like e equals p squared over 2r. Okay? And then when you're actually forming the solutions, you actually have to choose plus in one set and minus in the other in order to avoid things blowing up. Okay? All right, so okay, now I don't have to go back and say this later on, but does everybody see how these reduce to the zero momentum case? Okay, again, you have to take e equals mc squared, set all the p's to 0, and then reduce this to minus mc squared, or minus mc squared times ct over h bar. Or no, minus mc. Yeah, I wrote that wrong. P mu is minus mc 0, 0, 0. And then you get another c from ct here. All right. That was going to be a homework problem, not anymore. Yeah.
So those are the general solutions, the most general solutions, assuming.
It's a set of 4 linearly independent solutions with the given momentum, p mu. Okay, you can pick a different momentum, and you get a different version of each of these for different momenta. But for a given momentum, these are 4 linearly independent solutions, which is what we would have expected. In the same way that we've got 4 linearly independent solutions in the zero momentum case. Okay, so coming back to spin up and spin down, the form of sigma z is actually really simple in our convention, and of course all of this is conventional. These are just minus 1, 1. And so if you take this matrix and you multiply it onto, say, this vector, all right, well, it's just going to assign a minus because these two terms are non-zero, and those are the two terms that this matrix are going to pick up off the diagonal with the minus. So what we find is that SZ on psi 1 rest equals h bar over 2 psi 1 rest. And then similarly, SZ on psi 2 rest equals minus h bar over 2 psi 2 rest. Okay, everybody see that? Say it again?
The first one should be negative, the second one should be positive.
Yeah.
Yeah, exactly. Thank you. I can do things backwards. That's what I meant. Yeah. And then similarly for these two. So this is going to be spin down along z, spin up along z, and then this is where it gets hard for me to see it. This will be spin up along z, spin down along z. Everybody see that?
Yeah.
Okay, it's whenever you have the 1 and the 3 that you pick up a minus.
3 is there.
Okay. So the free particle, or the solutions to the Dirac equation at zero momentum are actually eigenstates of S sub z. However, the solutions to the Dirac equation for non-zero momentum aren't. Now this isn't just some trivial observation. This is actually going to take us somewhere very important. Very, very important. So if you want to understand the Higgs mechanism, pay attention. All right. Can everyone see, just pick on one of these, say this guy, that this is not an eigenstate of this operator? The problem, of course, is this guy right here, being non-zero. If I apply this operator, this term gets a minus sign and this gets a minus sign. If these were the only two that were not zero, you would have an overall minus sign, but this guy gets a plus sign. So you got minus this term, plus this term, minus this term. You can't pull that out as an overall sign. Everybody see that?
Oh.
Raise your hand if you don't see it. You don't see it? Okay. When you hit this spinner with this matrix, the first term gets a negative, the second term gets a positive, the third term gets a negative. Okay? So this is going to become minus, plus, minus. I can't write that as an overall negative sign times this, because that would make all of them negative. Okay? So generally speaking, these solutions do not represent SZ eigenstates. If I see that. However, consider over here. Consider taking our z-axis to be along the direction of the momentum. So if we say that our momentum only has a z component, there is no x and y component, so this particle is only moving in the z direction, then look at what happens. The offending terms disappear. So in each of these solutions, as long as px and py are 0, we don't get the stationary particle solutions. They're still interesting solutions, but they're now eigenstates of S sub z. So it turns out that if you want to work with these solutions and you actually want to use some spin orientation to classify the different solutions, as say spin up and spin down, you can't just pick an arbitrary axis in space. Okay, you could do that for a particle at rest, and you might have expected so, because a particle at rest doesn't care about any direction over any other direction. There's no special direction. But once a particle's moving, the three spatial directions are not on equal footing, because one of them is the direction of motion, and then the other two are perpendicular to it. And all we're seeing is that if we choose the z-axis to be along the direction of the momentum of the particle, then we can actually interpret each of these as spin up or spin down along the momentum direction. Okay? These are what are called Helicity eigenstates. Where helicity is the spin along the direction of the momentum. So in quantum mechanics, you often think about spin sz, the z component of spin. And of course, that was an arbitrary choice. You could have picked sx or sy. We just conventionally, for example, when solving the hydrogen atom, picked the z component. Right? But here, there is a special component that's easier to work with, and it's the spin along the direction of motion, which we call the helicity. Now, characterizing the states of a particle or antiparticle according to helicity is almost just like characterizing them according to their spin along z, with one very crucial difference. Okay? And I want to show you what that difference is, because there's some very interesting physics in this. David, you got a question?
Yeah, so I just want to make sure that even though we're doing this, we're still not certain about our full spin. Because, like, it's...
Sure, oh, yeah. Sorry, you're right. And I want to be careful. I'm going to draw some pictures, and I'm going to keep drawing them parallel or anti-parallel, but that's not the right way to think about it. So in this case, if I had my spin, like say that, the component along the momentum would be positive, but of course the entire spin can't be aligned with the momentum axis, because then you would know the transverse components are 0, and then you fully know that all three components of the spin, which like last time we said we can't do.
So we try and maximize how much it's sitting on?
Well, you don't have to try. Quantum mechanics only allows you h bar over 2.
Yeah.
Where the total where the total spin is the square root of 3 over 4 h bar. Square root of 3 over 2 h bar. Okay, so you don't have to maximize. I mean, quantum mechanics don't even give you one answer, or two, plus or minus. Okay. All right. So, I'm going to regret erasing these, but whatever. Okay, so so this is actually a lot. I know a lot of what I've been writing on the board is like, it's terrible looking. All these equations and all these matrices and vectors. Oh my God. But this is actually interesting. This is, I think, you can. What I'm about to say, you can kind of wrap your head around as I'm saying it. So this is the part of the lecture I actually like. So first of all, if we want to characterize the particles in a theory based on the z component of spin, so for example, using S sub z, if the particle has, say, spin up along z, so the eigenvalue of the spin along z is plus h bar over 2, we can change this. That's why we call it a degree of freedom of the particle. We can change the z component of spin. All right? How would we do that? Well, let's take a coordinate system. And let's just say we've got a z component of spin sitting like this. I can change the sign of the z component of spin with a rotation. I literally can take my axes and rotate them such that afterwards the z-axis is pointing down. I'm just changing coordinates. I'm not doing anything to the particle. But now, if I ask what is the z component of the spin of this particle, it's minus. Okay? Conversely, you can physically think of this as a particle in a single coordinate system could have it spin up or have it spin down. Okay, there's two possible states it could sit in. Now, helicity is the same way. And I'm going to denote helicity like this. That is the spin along the momentum direction. Okay, a lot of people call it little h, which is not the not reduced Planck constant, but helicity. But I'm just going to call it this. I think it's a little more intuitive. So if SP is plus h bar over 2, then what we have in mind is that you have a momentum and the spin, and again, David, I'm just going to draw it parallel, but just bear in mind there's some angle because it's never perfectly parallel. The spin is aligned with it, but this is something that I can change. Because if I have a particle moving to the right with some momentum p, I can haul ass that way, and if I go fast enough, that particle will appear to me to be moving this way. So I can actually, so I do this with a rotation, I can boost, and in doing so, reverse the momentum. But reversing the momentum does not reverse the direction of spin. Hold on. Okay? Again, a boost is just a coordinate change. That's what we learned in the in special relativity. Lorentz transformations include boosts and rotations. They're just coordinate changes. Of course, this includes time, where spatial rotations don't. Okay? So does everybody see that characterizing things by spin along z, spin up, spin down, you can change that. It's perfectly analogous to characterizing things by spin along p, because I can reverse that if I like. Okay? But what's the difference?
So I was having a problem with the rotation on the first part there. Like, how did you rotate that to get from the first frame to the second, like rotated frame?
Oh, yeah, sorry, you're right. Wait, did I?
Just reverse X.
Is it just zero?
No, he's right. Should be that. What? Yes, I want to have right-handed coordinate systems in both cases. Otherwise, I'm doing parity, which we'll talk about later. Yeah.
Is I mean, one, you're doing only spatial components, but this time you're involving time. So that seems like really wonky.
It seems wonky?
Yeah, I mean, to like be able to get the change in spin sign, you have to involve a time transformation.
But in special relativity, who cares? I mean, it's an allowed transformation. I mean, you might not like it. I didn't ask, why don't you like this?
Well, it's not.
I said, what's the difference?
I mean, even though we like to, like, time is not the same as a spatial when we involve it in a coordinate transformation. Because
Like hell, you say? What are you, Newton? Dude, Einstein came and gone and died.
he's got
And they made a
different
movie.
sign in the metrics, they're not the
Walter
same.
Matthau Pike was a lobster.
So does this kind of fall apart if we're talking about photons?
Yes! What's the special case where this whole thing falls apart? When you have massless particles. If you have a massless particle, this cannot happen. If something is hauling ass to the right at C, there is no boost. There's no Lorentz transformation which can reverse that. Remember, getting the momentum to change direction means boosting at a faster velocity in the other direction. Or sorry, along the same direction. Okay, if I want to get this to go backwards, I have to be moving that way faster than this is. But if something's moving to the right at C, I can't boost to the right at a speed faster than C. I cannot reverse it.
I have a question about the rotations. Is it something just because we're using this representation, but I feel like since we say it has to be h bar over 2 or negative h bar over 2, we're restricting ourselves to a 90-degree rotation, not continuous. Because if you really can't rotate that by a continuous amount, because then you're changing SC down low, you're just flipping the sign. Because if we've guaranteed that it's going to be h bar over 2, we can only do a 90-degree rotation.
Yeah, and so all I'm trying to illustrate is that you can switch plus to minus. Okay, if you do a rotation by something that's not 180 degrees, then you will generally mix up the components. Okay, but all I want to illustrate is that you can switch from plus to minus. And to do that, you need a 180 degree. Well, you need a rotation of all three axes. Okay.
And if you didn't do 180, then your SC wouldn't be defined.
These are quantum mechanics questions. Let's defer this until a later. I mean, you should learn about this in your quantum course, but
Yeah.
you know, but I don't want to get hung up on that because I'm not going to think about SZ. This is not where we're going to take. We're going to talk about helicity. So I want to focus on this. Okay. For massless particles, I can't do this. Now I want you to think about that for a minute. Here, and when these are massive, if I start by saying, oh, I've got plus h bar over 2, I know that there was always an option, or there is the option of switching that to minus h bar over 2. However, for massless particles, the helicity is fixed. It is an unchangeable characteristic of the particle. In many ways, it's like the total spin angular momentum. Remember, if we say a particle is spin a half, you can't change that. You can change the z component. All right, you can change it by changing coordinate systems or by just taking it and putting it in a magnetic field and rotating the state of spin. But you can't change the fact that its total spin angular momentum is 1/2 or 3/4 h bar squared. That's the eigenvalue. Right? So helicity for massless particles plays a very different role than it does for massive particles. In fact, if I say that I have a particle, if I say everything about these two particles are identical, but their helicity eigenvalues differ by plus or minus h bar over 2, I might as well call them different particles. Because there's no way you can take one and turn it into the other via some dynamical process. They are legitimately different particles. That is only true for the massless case.
So for massless particles, can we say helicity is conserved? Or is it more like an
You can say it's conserved, but conserved is usually a more powerful statement where you can account for the change in terms of some flux. This is just a fixed value. It's constant, is what it
So it's
is.
more like the fundamental chart.
Yes, yes.
So, like, if you reflect light, like, how does that interaction work at, like, the moment of reflection to, like, a beam of light? Because I'm just trying to think, like, does both the spin and...
So if you want to reflect light, that's a very, very different process than what I'm talking about here. So maybe you should think a little bit less about actively changing the spin states. I thought you guys were leaving at noon.
No need to be there.
You're going to miss all the fun. Think less about actively changing things and versus just passively changing things with a change of coordinates. And then there's no bouncing off of light. Like literally, if light's moving in a direction, no coordinate change is going to change that. All right? Okay, so what I want to do now, though, is I want to go back to the counting that we did much earlier in the previous lecture where we talked about Wigner's classification. Because what seems to be happening here is, for massive particles, we have these 4 states described by the Dirac equation, right? We had spin up, spin down for the particles, and spin up and spin down for the antiparticles. But for massless particles, okay, it's either spin along P or spin anti-along P, but once you've picked it, there's no more freedom. Okay? And then we have particles and antiparticles. So somehow we're losing degrees of freedom when we go to this massless case. So let's see if we can actually see that in the Wigner classification argument. So in the Wigner argument, remember what we said was, we have to keep P mu constant. Okay, because the Klein-Gordon equation essentially tells us, uses up the degrees of freedom in choosing the overall momentum, and then what you're trying to do is figure out what freedom do I have left to specify the state after I've already fixed its momentum. For massive particles, we could pick the rest frame as an easy frame to work with. So if m is greater than 0, we could just pick the rest frame, in which case this becomes MC000, and we can immediately identify that to keep that whole vector unchanged, we're dealing with rotations in 3 dimensions. And that's where we said that you could carry over the whole SO3 angular momentum story to characterize massive particles, even though we're working in relativity. So their angular momentum, if it's a vector, or spin 1 is 1, 0, minus 1. If it's spin a half, it's plus a half, minus a half. Okay? However, when the mass is 0, the rest frame is not allowed. There is no rest frame. So if we want to do the counting of how many degrees of freedom we have, we can't use this simple vector. But fortunately, there is a simple vector, a simplest vector we can use, and that is to say, let's just have the particle move only along the z-axis. So if the particle only moves along the z-axis, then its momentum 4 vector would look like that. You might say, wait a minute, why are you putting E here instead of P? Well, these 2 things have to be equal. So I'm just going to call them the same thing. They have to be equal because P mu has to be 0 for a massless particle. Remember, normally this is equal to mc squared, or m squared c to, m squared c squared. But it has to be 0 for a massless particle. So these 2 things, squared have to subtract to 0. But if I want to keep this thing invariant, go ahead.
If you said you're moving in the z direction, why don't you put it in the x?
Oh, sorry, in the x, yeah, sorry.
Okay.
Z, x, y, it doesn't matter. So x direction. I can put it in the z direction, it doesn't matter. I just want to keep my zeros right next to each other, that's why I said that. Okay. But the key thing here is, what transformations leave this vector invariant? Yeah, all I can do is futz around with the 2 zeros. So this is essentially SO2. And the problem is that SO2 rotations in a plane do not give me the freedom to reverse the direction of a rotation in the plane. So what I mean is, if I have 3 dimensions and I'm rotating in the xy plane, say counterclockwise, okay, so if I use a right-hand rule and define that as up, I can do a rotation that effectively reverses the direction of this, but I have to rotate using the z-axis. Yeah, I either have to rotate in the xz plane or in the yz plane by 180 degrees, and that will reverse the orientation of that spin. Here, though, if all I have is x and y, and the only thing I'm allowed is rotations in the xy plane, I'm never going to be able to reverse that.
Can't you just go the opposite direction? Why can't you?
So there's a thing that's spinning, and I'm taking the coordinates and I'm just rotating them. Not a time-dependent spinning.
Oh.
I'm not going to a rotating frame. I'm literally just taking the coordinates and I'm doing this or this. Okay? So here I literally take them and go like that. But here all I can do is just change this.
Okay, I see.
Okay, so I'm just trying to show you that the Wigner classification works to explain this loss of degrees of freedom for the massless case. Okay? What's interesting is that this result actually applies to particles of any spin. It doesn't necessarily have to be spin 1/2, because if you're spin 1, you still only have the degrees of freedom of rotation in a plane. So whereas with spin 1 particles that are massive, we would expect 3 states plus 0 and minus 1. For massless spin 1 particles, we only have 1 state. Okay? So now, oh my God, there's so much to talk about. Okay, so we've kind of got this idea of, all right, helicity is an interesting concept, especially for massless particles. Is all of this kind of hiding in the Dirac equation? Is it already there without having to draw all these pictures? And it turns out that it is. And when I show you where it is in the Dirac equation, we're going to encroach upon one of the most confusing ideas in this subject, and that is the notion of chirality, which is different from helicity. But it's very confusing. Most people are like, oh, chirality and helicity is the same thing. They're very, very different things, except for when particles are massless. So what I'm going to do is explore this in the context of the Dirac equation. So if we go back to the Dirac equation and we think about what boosts look like, so remember we built these little sigma generators of Lorentz transformations by taking the commutator of the gammas. So if I do a boost, which is having one of the gammas be 0 and the other one be a spatial, then this just comes out to I over 2 sigma I minus sigma I 0, 0. And if I do a rotation, taking both of these to be spatial, this just comes out to be 1/2 epsilon I jk sigma k 0, 0 sigma k. I don't distinguish between upper and lower indices of the sigmas. So, in thinking about how things transform under boosts and rotations, we can already see that it would be useful to take our 4-component spinner and think of it instead as two-component spinners, which I'll just call plus and minus. Okay? Plus to remind myself that the upper two transforms under boosts with a positive sign, but the lower one transforms under boosts with the opposite sign. They both transform the same way under rotations. Looking at psi plus and psi minus separately, they're 2-component spinners. So if I just say psi plus, I'm referencing a 2-component spinner. And if I reference psi minus, I'm referencing a 2-component spinner. These are called Weyl spinners, or chiral spinners. Okay? They're not Dirac spinners, because Dirac spinners are 4-component things. All right? But now what I want to do is, using this language of psi plus and psi minus, I want to go back and write the Dirac equation and see what it looks like in terms of psi plus and psi minus, instead of just in terms of a 4-component psi. So if I do this, the Dirac equation, and I'll actually look at the Dirac Lagrangian, from which we can, of course, derive the Dirac equation. This guy becomes the following: h bar c I psi plus minus d mu sigma mu psi minus plus I psi plus dagger d mu sigma bar mu psi plus mc squared minus dagger psi plus psi plus dagger psi minus.
Confused on notation.
Yeah, I haven't told you what up. So sigma mu is a 4x4 matrix, which, depending on the value of the index mu, is either the identity or one of them. Sorry, it's a 2x2 matrix. These are 2-component spinners. So I should be acting on them with 2x2 matrices. So if I have sigma 0, I'm going to use the identity, and if I have a sigma I, a spatial index, I just use a Pauli matrix. And this guy is the same, except I use minus the Pauli matrices. And don't get too hung up on this. It's not that important.
What does, like, when it has the minus in the bottom, is that 2?
This?
Is that a 2 tensor?
This is a 2-component spinner. This is actually the adjoint spinner. Why, it's part of the adjoint spinner. So you guys have to remember that.
Psi minus dagger.
Okay.
So
That makes so much sense.
So you remember the definition of the adjoint spinner. Okay, we actually know what gamma 0 looks like. So if we write our psi to be psi plus psi minus, then you can show that psi bar is just psi minus dagger, psi plus dagger. So the psi bar actually reverses the psi plus and psi minus. Okay? There are details to this which I'm leaving out, but it's not important because I want to get to the punchline. So what happens is when you take the adjoint, you actually swap these two. But the sigma matrices are antisymmetric. They're not diagonal. So it switches them back. So that's why we end up with a pairing of minus minus and plus plus. Okay? The adjoint switching is canceled by the action of the sigmas. However, for these terms, you have the adjoint which switches plus and minus, but that's it. So when you take this adjoint spinor right here and you combine it with psi, which looks like this, you're pairing up minus with plus and plus with minus, and that's why the mass term looks like this. Okay? The punchline is the following. If your particle has a mass, you must have psi plus and psi minus. Otherwise, you can't make this term. But that means you're working with a 4-component Dirac spinor. You have to be. However, if the mass is 0, you can use psi plus or psi minus by themselves. And this Lagrangian makes perfect sense. Because if m is 0, I don't need this term, and then I can just say, I want one of these or the other, set 1 to 0, and then do physics with just psi minus. Or do physics with just psi plus.
Would you ever have both in the m equals 0?
Say it again?
Would you ever have both in the m equals 0 case?
You can, you certainly can, but I'm saying the option of only using one is only afforded to you if m is equal to 0. But if m is equal to 0, then you can use the Dirac equation for a 2-component object. Half the degrees of freedom of the Dirac case, which is exactly what we've been talking about with the chirality story, or the helicity story. Okay? You cut down plus or minus h bar over 2 to just specifying the helicity, and that's it. And you can't change it. Now, yeah.
So is that or is it XOR? Like, can you use both in this case?
That's what he just asked. So you could use both. There's nothing forbidding you from using both. But the point is that the freedom to choose only one is only afforded to you if the mass is equal to 0. Okay? So what does it mean to work with psi plus or psi minus? So what is a physics? What kind of physics are you describing if you choose to just work with the psi plus part? Well, that's describing a particle with positive helicity. A massless particle with positive helicity, which you know can't be changed. So you can work with psi plus and not have to worry about physics contaminating it with psi minus, because you can't. And conversely, working with psi minus would be working with a particle with a massless particle with negative helicity. If the particle has a mass, you can switch the helicity by changing your reference frame, which is again why we have to have both helicities to describe a particle with non-zero mass. I'm just trying to I mean, I know these ideas are abstract, but you see where they're all pointing towards the same conclusion. Who had their hand there? Yeah.
So if we have a massless particle and it has a psi plus and a psi minus,
Yes.
we have this mixing of the positive and negative helicities. Is that what's going on?
So if you have a massless particle, you can take two massless particles of opposite helicities and combine them into a composite state, which effectively is massless and has both helicities. Okay, but there's not a fundamental particle that's massless that has both helicities. That's too many degrees of freedom. I mean, it's too many degrees of freedom by Wigner's classification. So we have to. So I want to talk about fundamental particles, not composite states. You can certainly combine two massless particles with opposite helicities and get something that has both, but fundamentally, no. But that composite state would be described by a Dirac Lagrangian including both of these,
Right.
but with zero mass term.
So if you chose to use both plus and minus, boundary conditions or something, tell you that one of is 0.
If you chose to use,
If you chose to solve the equation with both plus and minus, one of them would, you just solved one of them to be 0, essentially.
So, well, no. I mean, if I want to use this equation with both of these, okay, for a massless particle, or for massless particles, I am describing a two-particle system. Is what I'm getting at.
By definition.
Yes.
So you wouldn't describe one particle.
No. Yeah, that was what I was trying to get across with the answer to Peter's question. So if you're massless, then this describes a particle and this describes a particle. If you combine them, you're just describing a two-particle state. One of positive helicity and one of negative helicity, which you can work with, and there's a Lagrangian for that. It's right here. Okay. But fundamentally, one particle at a time, you would either pick this or pick this. Okay? All right, so I'm skipping. Okay, so in the last few minutes, I'm going to try and bring in maybe one more idea, because this is not enough. And it's well, yeah, I'll bring in this idea, and then we'll pick up with this next time, and hopefully be able to scoot through the end of the story so we can move on to the more interesting part. You might have noticed that everything that I've said so far, and this is where David Schmidt should really be in the room because he always has his eye for issues like this. Everything that I've said so far has kind of worked out because of the form of the gamma matrices that I chose. Okay, for example, the way that sigma mu nu's look, okay, is because of the particular gammas. If I pick a different basis for the gammas or a different representation of the gammas, the sigma mu nu's look different. The form of the Dirac equation looks a little bit different when you actually plug in your gammas. So you might ask yourself, is this just an accident of the particular representation that I chose? If so, that's not really something we should take serious. Because a representation is just like a coordinate system. You can pick any representation you want. You should still be able to describe the same physics. So it turns out there is a way of describing all of this that is independent of the explicit representation that you're working with. And that is to define gamma 5, which you saw in your homework. So if you recall, gamma 5 is defined as minus I, gamma 0, gamma 1, gamma 2, gamma 3. The only conventional freedom in choosing gamma 5 is this sign right here, and it doesn't change anything. But it is always going to be gamma 0, gamma 1, gamma 2, gamma 3 times I, where these are the gammas in whatever representation you choose to work with. It doesn't matter. Okay? For our representation, gamma 5 looks like this. I know. It would look different for different choices of representation of gamma. But for us, it looks like this. So having this, we can immediately form projection operators. If I add this thing to itself, this goes to 0, this becomes 2, dividing by 2, this just becomes, likewise, P minus just becomes that. Who cares? Well, this allows me to write psi plus is P plus psi, and psi minus is P minus psi. So I can actually define my Weyl spinors as a projection of the Dirac spinor using either P plus or P minus, defined in terms of gamma 5. These definitions you can use for any representation of the gammas. In fact, using this definition of gamma 5, you can show that this is a projection operator. That is, that it squares to itself. Okay? Without appealing to an actual matrix form. I mean, if you square this thing, you'll get 1 plus gamma 5 squared plus gamma 5 plus 2 gamma 5. But you can use the properties of the gamma matrices from the definition to show that this is still a projection operator. Okay? So the role of gamma 5, that matrix which you saw in your homework, is first and foremost to give us a representation-independent way of defining these chiral or Weyl spinors from the Dirac spinor. Okay? When we come back next time, we're going to take all of this and relate it to the story of parity and what a parity transformation would do. Because that's very intimately tied to this whole idea of changing one helicity state into the opposite helicity state. All right? We'll talk about that next time.
Where are we meeting? Oh, yeah.
Could you also say that?
What do you think I could pull out?
Now, Helicity on the stage.
I see
Mr. Patrick, is this actually?
You can say it, but there's no context. It's like saying, is he going to spin on this? You can say it, but it's no.
You're like,
For example, whether it's massive or massive, it's just like, I don't know. Here, no, it's like one stupid, it's like
one stupid ass.
interesting because it's very different. So it has non-trivial implications.